So our next subject is discussing the probability of error for BFSK, and we follow the same method like we have followed in our previous examples for ASK and BPSK, where we say that probability of error is defined by a general formula that says half ERSC, which is a complementary error function of gamma max squared divided by 8 power half. And we have already seen that gamma max is given by 2 over n naught, which is the reciprocal of noise power spectral density, integral from 0 to t of p squared t dt, where p of t is given by x0, x output 1 minus x of 2, which is the two signals that we are transmitting. And we know that x1 for FSK that represents simple 1 is represented by a cosine function of amplitude A with a change in omega of t, where we know that we can represent it as well here as a cos of omega 1 of t. This omega 1 is the one that is our omega plus some differential angular frequency, and our symbol 0 represented by x02 is going to be represented by another omega 2, which may be represented as a cos omega minus delta omega of t. So these are the two frequencies that we are using to transmit our frequency modulated signal, and therefore from this point we can be able to evaluate the gamma max. Gamma max squared is going to be found by following the same procedure, 2 over n naught, integral from 0 to t of, in fact, we should evaluate this from what we have already obtained here, and we see that this equals to a. We can say take this version and this version of cos of omega plus delta omega t minus cos of omega minus delta omega of t. So when we square our pt, this means we square this function and we square this expression, and that is what we are putting now here. And when we square this, we can put a squared outside, and we can consider this one to be our normal quadratic expression that says this is going to be cos squared of omega plus delta omega t plus cos squared omega minus delta omega t minus 2 cos of omega plus delta omega. So that is our expression, and we are integrating it with respect to dt, and from our experience we have already been able to evaluate this expression. So I can carry this and put that bracket there, and therefore introduce the integral here and introduce the integral here, such that we know. So I will just break this down. So we know that when you break this, you get a half of 1 plus cos 2 omega plus delta omega of t. That is our integral, first integral, and the second integral will follow the same idea, cos of 2 of t dt, and the last one would take the shape of, remember this one is cos a cos b, and we know that cos a cos b gives us a half cos a plus b plus cos a minus b, and therefore when we introduce that half, we get cos this plus a, this one we get 2 cos 2 omega, and we say this minus this, we get cos of 2 delta omega dt. So we will now want to simplify this further and see how it becomes. So what we know is that when you integrate, this one becomes sine, and we have already seen that this term goes to 0 in the past, and this term goes to 0 in the past. We have seen that, and also this term will go to 0 as well as this one when you integrate, because we know when you integrate, cos of 2 omega becomes sine of 2 omega divided by 2 omega. There is t there, there is t there. So we say that this value is way bigger than this value, therefore this term tends to 0. Similarly, these terms, when you integrate with respect to time, you get sine of 2 delta omega divided by 2 delta omega, and again this term, the denominator is way bigger than this term becomes 0. So we are left, after the entirety of this integration, we are left with the 1 dt t, and when you integrate 1 with respect to dt, you get a t, and from the limit of the upper limit of t, we are able to say that our final gamma max squared will become our constant here, 2a squared all over n naught. We have seen this term becomes 1 over 2t, this term becomes 1 over 2t, and this term, these two terms become 0, so plus 0. So our final gamma max squared becomes half t plus half t becomes 1, and we say when you normalize, we consider t to be of division 1, we have our gamma max squared being 2a squared all over n naught. Now we remember that our expression for probability of error was given by 1 over 2 ERSC of gamma max squared, which is this value now, 2a squared all over n naught, was divided by 8. So when we break this expression further, you can be able to say that this is equals to 1 over 2 ERSC of a squared over 2 dot these two I want to divide it by 2 divided by 2 4. So this we have 1 over 2 n naught, because I have broken the 4 into 2 times 2, so that we can express this term as E. Therefore, the final expression for probability of error becomes 1 over 2 ERSC E all over 2 n naught. That is the expression for probability of error of BFSK. That is our final solution. Yes.